Katoa, everybody. I'm Jen Purdy. I'm going to just introduce our speaker today. I'm at the Centre for Sustainability. So welcome to this joint Centre for Sustainability Otago Energy Research Centre seminar. Our speaker today is Dr. Ian Mason, and he's going to talk to us about sustainable energy storage. I will shortly introduce Ian, but first of all, just a little bit of housekeeping. So Ian's going to talk for about 40 minutes, and then we'll have time for questions afterwards. Please either write your questions in the chat section and when they occur to you, and I can read them out afterwards, or alternatively, I'll just ask for verbal questions at the end. And if we get to that, just use the put up your hand and I'll call your name. And just be aware that this is being recorded and will be available on our YouTube channel later if you want to refer anyone to it. So I'd like to introduce Ian Mason to you. Ian's a Renewable Energy Systems Engineer. He's been teaching at the University of Canterbury for many years. He created the Renewable Energy degree, created and taught courses on sustainable energy systems, modelling and analysis, and sustainable engineering for a changing climate. His research outputs include publications on transitioning New Zealand to 100% renewable energy, offshore wind, hydrogen, and other topics. He's a co-founder of the New Zealand Offshore Wind Working Group and is presently researching the role of offshore wind in the energy transition. So Ian, we very much look forward to your talk on sustainable energy storage. Can I just ask that people keep muted when they're not actually speaking? That would be great. Okay, over to you, Ian.
Okay, just get my full screen up, and hopefully you'll be able to see that in a second. Okay, well, thank you very much, Jen, and it's a great pleasure to be speaking to you all today. Even though I'm in Christchurch, I do feel very connected with the centre. I check the emails regularly, and everything from the staff club specials to the latest research projects, and like, I've really enjoyed getting to know you all and finding out about all the great research that's going on in the centre.
Ian, can I just interrupt you there? We're not on full screen yet. Can you try putting that on slideshow?
It's on my full screen at the moment.
Is it on as a slideshow?
I will just go back. Right.
Just select the thing at the bottom of your screen that looks a bit like a wine glass.
Yep, that's what I did. Yeah.
It's not showing up. Yeah, just press that.
I think that's trying to do it now.
Exit the share and restart it again once you're in full screen mode.
Okay, how's that? Oop.
No, if you stop sharing the screen, then turn on the slideshow and then start sharing the screen.
Okay, right. Okay. Okay, I'll try this again.
Big, maybe you could drag down the click to add notes bit to make it a bit bigger.
Okay.
That's better.
Okay.
Maybe even the one on the left as well, perhaps.
Yeah, get rid of that.
That's good. That's great.
Okay. Yeah, sorry about the technical difficulties here, folks. Right, so I'll start again. Sustainable energy storage. And here's a quick overview of what I plan to cover today. I'll first start with some optimal combinations of generation and storage, move on to evaluating options, mainly on an energetic basis. Then I'll move to Lake Onslow and discuss briefly some of the alternatives. Say a few words on social, environmental, and geopolitical issues, and then we'll draw some conclusions. But first, why storage? So Megan Wood spoke to the wind conference.
Right, now how do we make it noisy?
Sorry, are we, do we have a problem?
Could everybody please make sure they're on mute? Paul Bruce, could you put yourself on mute, please?
Oh, okay.
And also perhaps
yeah, there's
on closed video, because when you move around with your video on, Paul, it's very difficult for the rest of us to see this thing whizzing around.
Okay, so I'm just quoting Megan Wood spoke to the Wind Conference about a month ago, and she said this: New Zealand simply has to find a way to have decarbonised storage. Anyone who argues that we don't need to do this is not taking a long-term strategic view of what we need. And I totally concur with this statement. I'll just expand it briefly by saying that we need to see this as part of adaptation to climate change, and also about building resilience for the future, and particularly independence in our energy system. And I would also add that this facilitates the wise use of energy. And why are we interested in the wise use of energy? Well, I have 3 points to make here. Firstly, despite claims to the contrary, renewable energy is not an infinite resource. And we take into account the engineering realities, the materials that we need to employ to harness it and utilize it, then it's definitely a finite resource. Secondly, energy has quality, and this is from the second law, and there are two thermodynamicists there on the right-hand side. And I argue that it behoves us to use our energy wisely, the high quality energy as best we can before it degrades into low quality heat.
Hey, Warren, dirty bugger.
Sorry, I'm still getting people talking into this. Can people please mute? And thirdly, matters of social equity. So the argument here is that the better we use our energy, the more resources we will have left over to address issues of just transition. And there's a very good paper by Lambert, which is a good conversation starter, which talks about the relationship between energy, energy return on investment, and quality of life. So let's have a quick look at present energy storage in New Zealand. We have piles of stuff, we have tanks of stuff, we have tanks of stuff, and we have one geological storage facility for fossil gas. We also have a major resource in our hydro lakes. We have about 4,000 gigawatt hours of storage capacity, which is roughly 10% of our annual demand. And if gigawatt hours aren't something you're familiar with, just think of gigantic electricity bills, right? We have 4,000 gigantic amounts of energy there. In the images, we have a pile of coal on the left-hand side. Below that is the Miramar Gasworks with a pile of coal and a gasometer in the back. Then in the middle, we have Marsden Point with its tanks of petrol diesel. It's now an import facility, of course. Below that is the geological fossil gas storage facility in Taranaki. And then I'm sure you all will recognize Lake Tekapo on the right-hand side. This is part of our very big battery system comprising the hydro lakes. The challenge of renewables, of course, is they're variable. We can't call them up when we want them. They are partially predictable, of course, but not totally. So the supply and demand patterns are different. And we need something in the middle there to buffer between those. So that's where storage comes in. And in simple terms,
But it's not, and that screen shouldn't have anything to do with that. Why?
And this analysis applies to various forms of energy, electricity and heat. I'm going to talk today about electricity, but we can think about heat as well. The graph there illustrates the cumulative charging rate for a storage facility and the cumulative discharge rate, and you'll see there's a discrepancy between them. So at about day 100, there's a gap where charging exceeds discharging. So we need to accommodate that. And then further over about day 300, there's another gap, another major gap, and that's when the rate of discharging exceeds the rate of charging. So storage really needs to accommodate those two things. So the charge and discharge patterns are the same as the surplus and deficit patterns in a system. So a few basic ideas now from electricity systems. Firstly, we can minimize the storage we need by specifying generation over capacity. Some people use the term overbuild, but I tend not to use that because I think it's a little bit loaded, but we can discuss that later if people would like. Optimal combinations of installed capacity and storage exist, so we can find those. But the result of that is that we get energy spill. This is energy which can't go into storage and is excess to demand. So we have a few options what to do with that. We can send it to discretionary loads. These are loads which are not time dependent. We can use it to produce other energy carriers. There's a lot of talk about power to X, where X is various chemicals from hydrogen through to petrol-like compounds. We can have power to food technologies. We can put it into dump loads, which simply waste it, or we could curtail the production. Quick word on the range of storage technologies and particularly the timeframes. So I'm going to talk today about storage on the right-hand side of this graph, which is leveling the seasons. And in fact, I'm interested in leveling the years, so yearly and multi-year storage. If we move to the left, we have storage for weather, which might involve a few days or maybe a week. And so moving further to the left, there's night and day storage, balancing that. And then finally, there are power quality issues which require special types of storage. This is voltage, frequency, harmonics control, etc. So I'm going to talk about the right-hand side of this graphic. A couple of important concepts distinguishing between energy and power. So there's a little example there. If we have a 400 megawatt capacity, that's the amount of energy which the storage will hold. And 100 megawatts is the rate at which it can be discharged. So at maximum power, that will give us 4 hours of storage at maximum output. So we'll talk about this a little bit later as we go along. So I'm going to start with an example of how to design storage. This is some work which Alan Miller and I published a few years ago. The idea is that you increase the amount of generation, and that increases what we call the penetration, which is the amount of gross energy that is generated divided by the annual demand. So a ratio of 1 simply means that you generate the annual demand. And a ratio of 10 means you've generated 10 times the annual demand. Solve that for storage, and we optimized on 2 bases, the energetic and the financial. So EROI is energy returned on energy invested, and NPC is net present cost. Now let's have a look at the storage patterns which resulted. On the y-axis, we have fractional storage as a ratio of demand. It might be helpful to think of that as percentages. So 10%, 20%, 30% of annual demand. And then on the x-axis, that's just the years, starting with the 1st of January through to the 31st of December. So if you just look at this penetration 1.1, and I'm going to try and move my cursor. Hopefully you can see that cursor. Right, go away. Hopefully you can see the cursor there.
Yes, we can.
Penetration of 1.1 means that we've generated the demand plus 11% to cover the losses going in and out of storage. This graph starts at, oops, now we've got into trouble. This graph starts at there, and then it rises up to about 0.35 or 35%. Then it bottoms out here, which is around September time. And then it comes back up to where it started over here. Now, if we increase the generation and therefore increase the penetration, you'll see one thing that happens is that it flattens out here. And that's equivalent to it spilling over. You can have an analogy of a bathtub, for example, or a spillway of a hydro dam. And the more the penetration increases, the lower the storage requirement is. So by the time we get down to here, we've got less than 10% of the annual demand of storage. So that's what you do when you start increasing the penetration. Here's a close-up of one of those optimum spill patterns. So here we've got about 1.7% of annual demand for the size of the storage facility. And a lot of the time it's just operating at the very top level of the storage. So it's just fluctuating here. And there's a lot of spill going on. So there's a lot of spill going over the top of the dam, for example. But when it gets to the middle of winter and after the middle of winter, it starts to draw down the storage, and here it bottoms out. And that gives us the amount of storage which we require, which is about 1.7% of demand. Then it starts to fill up again during the rest of the year. We can quantify the spill patterns. This is starting at 1.5, and as we increase the amount of penetration, we see the spill is increasing, and it's also spreading more into the middle of the year. And so by the time we get to a very high penetration here, we've got spill occurring for a great part of the year. So we know when it occurs and we know how much is occurring. So looking at optimization, firstly on an energetic basis. So energy returned on energy invested is the amount of energy which we have generated from the system divided by the amount of energy it took to create that system. And the break-even point is 1. So below 1, the system is a net energy sink. And as someone put it, you might as well just sit there and look at it. It's of no use at all. In fact, it's going backwards. But if it's greater than 1, then we have a net energy gain in the system. And here we have an optimum of 1.5. So just a reminder, that's for a system comprising solar PV panels plus lithium-ion batteries. And then there's a law of diminishing returns as we go over here. So the optimum here is a penetration of about 4. Now looking at cost, there are 3 different patterns here, just 3 different demand patterns. And you can see they bottom out at between 4 and 5. So it's not exactly the same as the energetic evaluation, but it's pretty close. So and they can be moved so that they coincide. So we would say that our optimum system here is one which generates about 4 times annual demand, and that will give us the minimum storage. Now, there's another approach one can take where you specify the storage in advance and then you see what happens. So here's an earlier study, and this is based in the PJM network in the northeastern part of the US. And if you look at the map on the right-hand side, you might recognize New York on the right there, a couple of the Great Lakes. And so we're going right into the Midwest here. That served about 65 million people at the time of the study. So these authors had wind and solar, giving most of the generation, and they specified storages in advance. So they had hydrogen, chemical batteries, and electric vehicles. And the optimization was purely on a financial basis. So let's have a quick look at one of the results. This is a penetration of approximately 3. So generating 3 times the demand over 4 years. This green graph just shows how the renewables are fluctuating over time. And you see they're up and down all over the place, as you would expect. But there are a few gaps here, a few light patches. And if we look now at the storage, here it's pretty much full, and it's operating as we saw in the last one of the last slides there, pretty close to the top. But then there are times when it is drawn down quite substantially. So here it's drawn down quite a bit there, but there. And in this scenario, they had fossil backup generation. I think it was a gas turbine from memory. It doesn't have to be fossil, it could be any type of backup that you choose. And so that kicks in 1, 2, 3, 4, 5 times a year. And that coincides, of course, with the storages bottoming out there and there. So that's a second approach that we can take to generating storage. Now, I won't go through all of these graphs, but just like to draw your attention to this one. This shows in a little more detail what's happening at one of those difficult times when the backup had to come in. So the black line is the demand pattern there, so up and down. The green is the renewables. The grey shaded bit is where the storage is being drawn down. And we can see here that the renewables are low at this point, so storage has to be drawn down. And again, the renewables are low here, so the storage is drawn down. Then the red part is where the backup generation comes in. Now, there's another shade over here, which is a yellowy green, and that represents spill. So at this point, the renewables are supplying 100% of the demand. The storage is full. And so that is what we call spill, that's surplus. Now, that's for the centralized battery storage, and the other graphs show the other two storages and how they perform. So they perform somewhat differently depending on the type and the size of storage. So let's move now to how we might evaluate options. So this is on an energetic basis, and we're going to introduce a term on the left. So if you just focus on the left-hand side, that's energy stored on investment, or energy stored on energy investment. In this case, that is the energy stored in the system over its lifetime, divided by the energy that was used to create it and to operate it. And that's expressed as fossil fuel energy. So what we see here is that this is compressed air storage, and this is pumped hydro storage, and they're over 200. And then if we go down to the chemical batteries, lithium ion is the best at 10, and lead acid is the worst at 2. Now, there's a lot of information on this one, which normally you wouldn't see all at once, this is the energy returned on energy invested of the generation. So this is a graph of energy returned on energy invested for wind, solar, and other things. And on the x-axis, we have the storage energy stored on investment. But they've played a little trick here. They've changed this to the electrical energy stored divided by the electrical energy required to make and operate the storage system. So these numbers are bigger by a factor of about 3 and a bit. So let's start by observing the values for some of these storage options. So this is lead acid, this is lithium ion, so they're all fairly low, around 30 max. But then pumped hydro is 700, and compressed air is about 900. So those values, they're way off to the right-hand side of this graph. So this is a decision matrix, whether you should curtail the production of energy and not store it, or whether you should store it. And these are various fractions of the amount of electricity which is available for curtailing or storage. Here we've got wind, and they've got an EROI of about 88 or so. I think that's a bit high, but never mind, we'll just accept that for now. So what this graph tells us...
No, they just got us through.
Sorry?
Sorry.
Tom, can you mute, please?
Yes, sorry.
Yeah, so this decision matrix tells us that these lead acid batteries and the lithium ions right through to here, for wind energy, don't store them, curtail them. But for pumped hydro and compressed air, that's way off to the right-hand side. It makes energetic sense to store that energy rather than curtail it. Now let's come down here to their PV, which is about 9. And in this case, it makes energetic sense to store in some batteries, but not others. And it makes energetic sense to store it in compressed air or pumped hydro. Now, here's the argument. Making electricity from wind is energetically cheap compared to PV. So therefore, there's less energy invested in making that energy. Therefore, there's more scope to curtail it rather than to store it, because it's not worth spending the extra energy on these storages to store something which took a very low amount of energy to make, right? Now, if we then contrast that with PV, electricity from PV is energetically expensive to make, right? It's only got an EROI of 9. Therefore, it's worth spending the extra energy on the storages here, the batteries, etc., in order to not waste that energy, not to curtail it. And certainly it makes sense to store it in pumped hydro or compressed air. Now, I will update this now with some numbers from New Zealand so that we have for energy returned on energy invested for hydro. It's up about here. I think this is very optimistic for wind. The New Zealand figures peak at around 60, but they could be as low as 30, so somewhere in this range. However, in both cases for New Zealand, hydro, wind, and PV, I haven't put on here, but that's about 6 for New Zealand. It makes sense to store all of those with pumped hydro or compressed air. Now, what about hydrogen, which has received a lot of attention in recent times? This is from another paper, the Pillow one. The energy stored on investment, electrical for hydrogen stored in steel tanks is 4. So it's way down here. So it's not a starter in energetic terms. However, if hydrogen is stored in underground caverns, the ESOI jumps up quite markedly to about 80. Now, salt caverns are widely used and talked about in Europe for hydrogen. We don't have it in New Zealand, so we need to look for other options, and I'll talk about that in a little while. So that's the decision matrix, if you like, for whether you should store. And what we've seen here is that it matters what the generation is as to what your decision is about storage versus curtailment. So here's the story so far. We can find out how much storage we need, either by solving for it directly, or we can select it in advance and then observe the performance and specify some backup for those occasional times when it is needed. We can quantify the spill, and we know what the timing is, and utilization of spill is important because it'll increase the capacity factor of the generation, it'll increase the EROI of the generation, and it should increase the EROI of the whole system as well. Our analysis shows us that pumped hydro is energetically an excellent choice for storing surplus wind and PV, which we would have a lot of in New Zealand if we expand our renewables generation. So at this point, let's move on and have a look at Lake Onslow and some of the alternative options for New Zealand. And if you excuse me a moment, I'm just going to take a wee sip of green tea just to refuel. So I'll just be a second. So one of the big issues in New Zealand at the moment is the so-called dry year deficit. And this has been estimated at 3,000 to 5,000 gigawatt hours. Again, gigawatt hours, very large units of energy. And the New Zealand Battery Project has been tasked with finding at least 5,000 gigawatt hours of storage, maybe more. We should note that future storage will need to serve an electricity system with at least twice current electricity demand, so very approximately 80,000 gigawatt hours per year. And with a very high proportion of, my guess is that it'll be mainly wind, but there will be quite a bit of PV in there as well. And so we need to find out what's the supply-demand correlation with, of those for the future. Now, the New Zealand Battery Project was set up by the government, and they're considering basically 2 scenarios. One is Lake Onslow pumped hydro, and secondly, what they call a portfolio approach. None of these options can supply the storage by themselves, but it may be that a combination of these will do the job. So this is some smaller pumped hydros using hydrogen, having flexible geothermal, having a biomass system, and of course demand response. So the Lake Onslow scheme is illustrated in this graphic, and we'll just very quickly highlight some of the features here. The idea is to use surplus electricity or cheap electricity to pump from Lake Roxburgh or another reservoir, or maybe the Clutha River, through a powerhouse, through a tunnel, and up to Lake Onslow and possibly Lake Mannaburn as well. Now, as an engineer, a head of more than 600 meters is awesome. I'm so excited by this very high head for the hydro system. It's the sort of head that you normally only get in the Andes, places like that. And then when there's a deficit of electricity in the system, then the water is run back down the tunnel the other way, back through the powerhouse, and supplies those deficits. So this is a way of storing surplus wind and solar and then getting it back again with whatever losses are associated with pumping up and coming back down again. A few important figures. The capacity which has been identified as anywhere between 4,000 and 12,000 gigawatt hours for the Onslow and Mannaburn system at the top there. The power which has been mentioned is up to 1,500 megawatts to supply those peaks. And if we just look at that, if we take 12,000 and 1,500, then we could pump for, we could supply for nearly a whole year from the system. So that may well be a bit over the top, but that gives you an idea of the capacity and the possible use of the system. I think a more likely scenario is about 6,000 kilowatt hours, which would be 7.5% of future annual demand. And based on those graphs which we saw earlier, that ought to be sufficient, but we really need to model that. And that would run for about 4,000 hours at maximum output. So some points for discussion about Lake Onslow. I think the first point to make is that it is a two-way storage, and that's really important. It has the capacity to totally meet the dry year deficit. Now, this is the market side of it has been modelled, and what has been found is that it will lower the peaks, so those extreme electricity prices will disappear, and it raises the low price, so the very low prices will also disappear. So it will make a less volatile market or a more stable market. And I think that should appeal to certainly many, many users in the New Zealand electricity system, not only now, but into the future. One can argue that this is a very environmentally friendly storage system. It comprises water, soil, rocks, a bit of concrete, and some hydro plant, which we know about already. And if you compare that to the alternatives, it is a very, very environmentally friendly option. We've talked a lot about just transition. I think this would have a lot of societal benefits. It's a major job creation scheme. It's a big infrastructure project, which may take 10 or more years to build. We can expect it to have a very long lifetime, at least 50 years, but I would guess maybe 100, maybe longer. And then, of course, the lakes can be desilted if necessary, and it can carry on, it can be refurbished. In terms of cost, it has actually a very low capex per gigawatt hour, and I'll illustrate that in a moment with a graph which is coming up. On the other side of the argument, it is a very high expenditure in absolute terms. It's a billion-dollar project, and well, it's several $1 billion actually. From a technical point of view, the tunnel is very long, so the length of the tunnel as a ratio of the height or the head. So the head is only 0.026 of the length of the tunnel. That's very, very low for pumped hydro systems around the world. It does require that those surpluses to be made available somehow, or low-cost energy used in order to fill it, and those people have been exploring those various options. So I think that's more of a market design approach which is required there. We do not know the energy stored on investment for this. We don't know what the EROI of the system would be from this, so I think those things need to be found out. And the construction greenhouse gas emissions really need to be determined as well. I'll just make a comment there that the construction industry is starting to electrify. So the more the construction can be electrified using our highly renewable electricity, then the better it will be for the overall greenhouse gas emissions of the project. So now let's have a quick look at the portfolio options, the alternatives to Lake Onslow. So these two are two-way storages, which means they can take the surpluses and they can supply the deficits. Here's a comment from a 2015 paper. This is making hydrogen by electrolysis, storing it, and then putting it back through a fuel cell in order to make electricity again. Their comment, this type of storage is generally unfavourable for wind over generation, as it is energetically preferable to curtail the wind than to spend the additional energy to build the RHFC storage capacity. Now, we saw earlier that geological storage can improve the ESOI of the hydrogen option, but we don't have salt caverns in New Zealand. You've probably heard that last week the government announced, or MB announced, that they were granting $11 million for a study of geological storage. I actually had lunch with one of the lead authors of their paper, one at Canterbury, and he brought along rocks, some of these rocks, to lunch, which is kind of interesting. But we still don't know whether we have suitable geological storage in New Zealand for hydrogen. The question of leakage of hydrogen is really important. It has global warming potential over 100 years of about 11, or taken over 20 years of 33. So leakage of hydrogen from storage could significantly increase our greenhouse gas emissions, not to mention all the other safety issues around leakage of hydrogen. These authors have proposed that they would store about 50 million cubic meters of hydrogen in a geological store, cavern. This would supply about 37 gigawatt hours of electricity, assuming they used an open cycle gas turbine. So that's really a very small drop in the bucket compared to the dry year deficits, which we looked at earlier. Building pumped hydro somewhere else. There are a number of sites that have been identified, but these have much, much smaller capacities than Lake Onslow. I understand that these are mainly in the North Island and they're all on culturally sensitive sites. So I think there will be some issues there. No doubt this will come out in the New Zealand Battery Project's report, which is due in the not too distant future. Right, sorry, I've just got an interfering message here. Right, so the other portfolio options are all one-way storage, which means that they can supply the deficits, but we can't feed any surpluses into them. So using biomass, there's some comments being made about running the Rankine units at Huntly on torrefied biomass. Now, torrefaction is a process which dries biomass like wood chips and drives off some of the volatile material. One caution about this approach is that if people decided to import torrefied biomass, this could be environmentally very, very damaging. We don't want people cutting down Canadian rainforests or Polish rainforests and sending us their wood chips so we can do that. That would be bad news for the planet. However, I think if this is done using New Zealand biomass, then this could be quite a sensible transitional strategy while something more bigger and more permanent is built. Flexible geothermal. Now, geothermal plants are usually run pretty much at full capacity, but it is technically feasible to ramp them down and run them at part load. This is being done in Hawaii. And this means that the energy is being held back in the geothermal reservoir. And we actually modeled this back in 2013. The switching would be done perhaps on a weekly or even a monthly basis rather than on a 30-minute basis. So it would be slow switching rather than rapid switching. So that's another possibility if people can be convinced to run those systems at part load. Now, demand response, that's basically turning things off. There's been talk about interruptible hydrogen production in Southland. So that would use Manapuri electricity to make hydrogen, but they would stop doing that from time to time in order to release that. I just make the quick comment that Manapuri has an annual production of about 6,100 gigawatt hours, and it's I think its practical capacity is about 750 megawatts. So it's difficult to see how that can make us a major contribution to the dry year demand. It would have to be running for a good deal of the year in order to supply enough energy. On the domestic front, Michael and his colleagues have published on energy efficient housing and talked about how that can make a contribution. And I think that's great. I think we should be doing that. And I know that a grant has just been given to take that further. My only question mark would be, can it be done in a timely fashion? I think this is, any behaviour change like this takes many decades normally. We need to get on with this in the next 5 to 10 years. So certainly keep doing it, but can it deliver in time? So quickly now on some of the social and environmental issues. The just transition is key, of course. And I think there's an important question which comes out of the situation we're in right now. And that is, given that the goal is to avoid disastrous climate change, what is the appropriate balance between local environmental and ecological impacts and rapid real reduction of greenhouse gas emissions? So is there a middle way? And I think this would be an interesting debate for us to have. Maybe in the question time, people will have some views on it. My feeling is that we have now reached such a critical point with climate that we need to prioritise things which will reduce greenhouse gas emissions and build resilience and help us with our adaptation. On the geopolitical front, it's important that we minimise our reliance on some of these complex international systems. We've had the example of the global financial crisis, for example. We've had the example of COVID, and now we've got the invasion of Ukraine by Russia. And this has led to a lot of volatility, not only in the energy markets, but also in the food markets. So we really need to protect ourselves in the future from volatility in energy markets in this particular case, and build our own resilient and adaptive energy system. So where do we go to from now? Well, I think, firstly, what are the energetic and financially optimal two-way storage capacities for a New Zealand energy system? And I'd like to see this modelled in the same way that we did, that I illustrated earlier on. As I discussed before, we can solve for storage, or we can specify storage and then see, well, is there a role for backup options? And I'm sure there is. And it may be some demand side management. It may be a little bit of one of those other one-way options. So I think that's an important discussion for us to have, because the future won't be able to be modelled exactly. So we'll need to have some backup options there for sure. Is the present market system, and especially the industry structure, is this going to deliver on what we need to do for our long-term energy strategy? If not, what modifications do we need? And have we reached the point where climate change mitigation and resilience should actually be the top priorities? So in conclusion, when generation and spill are evaluated together, we can identify optimal combinations of those two. So generation and storage, and then utilising spill is obviously really important. I argue that it's really useful to express storage capacity as a percentage of annual demand. And that gives us a nice, easily understandable metric in which to discuss various options. Pumped hydro is a really great choice on energetic grounds. I would argue that environmentally and from a social point of view, it's also a very good choice. Lake Onslow could give us 7.5% of future annual demand. If we added that, the existing hydro into that, it would be 12.5%, which I think should be adequate. And finally, as we've seen from the Minister's statement, earlier in this talk, the political will to implement long-term energy storage is here. Quick acknowledgements. I'd just like to thank Malcolm Taylor and Will Barsley for some helpful chats over the years. And if you haven't seen Malcolm's presentation to the Auckland Energy Summer School in 2021, I would totally recommend that. Right, some references here if you'd like to follow up any of the papers that I've talked about. And thank you very much for your attention. I really look forward to comments, discussion, questions, and now hand the floor back to you, Jen. Thank you.
Cool. Thank you, Ian. That was really interesting. You covered a lot of ground. I'm sure there'll be lots. Well, I can see already that there's lots of questions, and I imagine we'll get cut short, but people can contact you individually afterwards if they need to. So
absolutely. I
will just start by reading out the questions in the chat, of which there is plenty, and we probably won't get through them. Someone's asked you to just quickly explain penetration again.
Sure. Okay, penetration of one is generating the annual demand only. So just generating the annual demand. The penetration of 2 is where we generate twice the annual demand. The penetration of 10 is where we generate 10 times the annual demand. Perhaps it's useful to explain that that's a kind of virtual generation because we don't know what we're going to do with the surpluses yet. So I hope that helps.
Right. The next question is, when you say environmentally friendly, have you considered the biodiversity destruction? I think you probably addressed that later on where you said there's pros and cons and balances and we have to perhaps prioritize carbon reduction. Is that right?
Sure. Yeah, no, that's a very good question. And what I'm saying here is that I think some difficult choices need to be made. I believe that we're at, and the Secretary General of the United Nations said this yesterday, he said we're at a really crucial stage, and particularly with climate change. So my argument is that climate change will destroy that biodiversity anyway. And so we need to get on with it in terms of mitigating climate change, adapting to it. And every engineering project has some ecological impact, and that's just unfortunate. So
I think we could argue that till the cows come home, back and forth.
Yeah, exactly.
And there's no right or wrong. I think the answer's in the middle somewhere, isn't it?
Yeah, well, that's why I suggested that we seek a middle way here. I would argue that let's say Lake Onslow goes ahead. Let's take all possible steps to protect the biodiversity and the ecological values which are there. But I think the priority has to be climate change and building a resilient and adaptive system.
Somebody asks if you know the quantity of storage percentage loss due to evaporation. I don't know if that's relating to Onslow or just hydro generally.
Sure, no, that's a very good question. I think a study has been done on Lake Onslow, and I'm not sure what the answer is. There will be a net evaporation or a net gain, depending on the climate. Being in Central Otago, there might be a net evaporation loss, but I'm only guessing. I would suggest you go and read Margie's thesis for a start to see if there's anything in there, and maybe contact Will Barsley to see if he's done any work in that space.
Brad asks, he agrees with you that the lake is already artificial in terms of Onslow, and that you might get a little bit of methane from flooding tussocks. But he also says that there's you're putting another hydro lake in the same area, so you have the same dry year problem with a similarly vulnerable solution. What do you think about that?
Sorry, that question...
in other words, you're building another hydro in the same area where all the hydro lakes will be dry at the same time. But I think the point is that you've pumped it up the hill earlier when you had a wet period. So I think that is probably the answer.
Yeah, absolutely. That's exactly the answer which I would give. This is not relying, I don't think it's relying at all on any inflows, any natural inflows. Well, there may be a little bit unavoidable coming in from that catchment. But basically, the water in Lake Onslow will be pumped up from the river below. So we're independent in that sense, and as you say, pumping up during a wet period. So yeah.
Eric Sharp asks about running baseload geothermal in relation to Onslow. Specifically, how do we retain the incentive to build high value, high reliability geothermal with a Lake Onslow plan? I think that's around how the economics of the whole market's going to work with such a behemoth dumped in it, isn't it?
Sure, yeah. Well, I think I've approached this mainly from an energetic point of view. So as I said at the beginning of the talk, wise use of energy. I haven't approached it from a commercial point of view, and I understand that each generator will have their own commercial interests to pursue. And I respect that, it's just that I haven't really talked about it. In terms of building more geothermal, I think that it has to stack up against our wind resource. There's a lot of work going into offshore wind at the moment, and our solar resource. So yeah, I wouldn't. If no more geothermal is built, well, that might just be a fact that we have all these wind and solar resources to utilize. Yeah,
I had a similar question written down about the Budashak work on the US, where you talked about gas being used 5 times a year, and around the economics of that, and that's a problem that's been mentioned by people like the Interim Climate Change Commission, who said we should, rather than being 100% renewable, would be better to go 99% renewable and keep a little bit of gas there, and it works out better for everyone, and the result is higher decarbonisation. But of course, the economics of keeping a little bit of gas that you use 5 times a year is something else, and keeping the pipes running as well for that.
Sure. Okay. So my response to that is that firstly, it doesn't need to be natural gas or fossil gas. It can be anything. It can be any type of, and it can be used, as you say, it was 5 times over 4 years actually in that scenario. Right. But I see a future where there's where the build-up of wind in particular will release hydro capacity to do a lot of these ancillary services, which they're not doing at the moment. I mean, they're doing some, like frequency keeping and that kind of thing. But I can see hydro moving. People have talked about baseload offshore wind, right? So I think baseload offshore wind is an interesting concept, but I know what they mean. That would release hydro capacity to do a lot of these other things. So we wouldn't need to keep gas to use it 5 times a year or 5 times in 4 years or whatever. We would have some hydro backup sitting there at part load in order to come in when required. And that could be Manapuri, so I see a different future to more of the same.
Yeah. We've got thousands of questions here. I'm sorry, we're not going to get through them, everyone. I'm just going chronologically, but rather than trying to pick and choose them. So maybe some sort of quick fire answers might be good, Ian, and then people can contact you separately if their questions don't get answered. But the next one is, what are some of the technical and economic consequences of operating a pumped hydro storage with a H to L ratio of 0.026?
The main problem there is the round trip efficiency. I imagine that will be quite, that won't be as good as some of the other ones, because you have to pump through a longer tunnel, but it's going to be a big diameter tunnel as well. So so we can't really draw any conclusions until we get the detailed hydraulic design.
Yep.
I think a good ballpark figure for the round trip efficiency is about 80%. Could be a bit lower, could be 75%, could be better, could be 85%, something in that ballpark.
Not too bad for a very large battery, is it?
No.
So you talked about compressed air storage. Somebody's asking about liquid air energy storage.
Yeah, I note that the New Zealand Battery Project has discarded compressed air storage for New Zealand. They're not considering it. One of the hiccups that I see about that is you've firstly got to have the underground cavern, and secondly, when you expand the air, it's very, very cold. So it heats up when you compress it, and then it gets very cold when you expand it. And often they use fossil gas turbines to heat it up again, which is not particularly good. So yeah, I don't have any more detailed comments about capacity than that, except I believe it's off the table. And
the question was about liquid air, which uses the cryogenic energy store. So it's a negative energy well.
Okay.
Look at Highview from the UK. They're starting to scale that up.
Okay, well, that's fascinating. I have to say that's something I'm not familiar with. I'd love it if you could email me some details, and we could have a discussion about that. Thank you.
Brad asks about the issue of Onslow being so far from the main demand sources and the pressure on inter-island transmission capacity. And yeah, what are your views on that?
I think that has to just be part of the mix. I think the reality is that, as far as I know, Lake Onslow is the only possibility for such large-scale storage, and therefore I think we just have to say we need to put the transmission capacity in there to deal with it. I don't know the details of the Roxford transmission lines, which are relatively close by, but I think it's the same issue as building a new wind farm. Offshore wind off Taranaki is going to require new transmission. That's just part of the deal. So I would just say, look, hey, it's part of the deal.
Yeah, and I think Dougal McQueen did quite a comprehensive study of all potential pumped hydro storage sites, and that was massively the best and biggest one.
Absolutely, yeah, I know Dougal's work, yeah.
Solace asks, how long can we maintain even the current grid ex fossil energy? I'm not sure what that means. Solace, you might want to jump in there.
Yeah, could you just explain a little more?
Maybe Solace is gone.
Yeah.
Okay.
Yeah.
Oh no, there he is.
The question is, we're sitting at the end of a chain which doesn't even have Marsden Point anymore, reliant on shiploads of fuel that's about to, well, is being in contention. And so the question is, on our own, how long do we maintain that grid? You think of all the utes that drive up to all the pylons and all the rest of that. And I'm asking the question, how long can we maintain even the existing grid? Are we dreaming? Do we have to backpedal and be more local?
Okay, I understand. Yeah. I've always believed that we're going to need the national grid for a long time. There will be people are interested in building microgrids for sure, but I think we need to plan for a future when we keep the macro grid in place, the national grid in place. We probably should get Transpower on this discussion, because I know they have a long-term planning vision, and they've been thinking about this for quite some time. So I would suggest we all get round the table with Transpower.
And I think I've seen Transpower's modelling, and they've got long-term projections of both of distributed energy and how that's going to grow. So I think they're planning that in detail. Look, it's past 1 o'clock and people are starting to leave, so I'm going to have to wrap it up. But thank you everybody for joining us, and thank you, Ian, for a really interesting talk. And please contact Ian separately if you have further questions. Thank you everyone for coming.
Thank you very much, Jen. It's been my pleasure.
Good.
Have a nice afternoon.
Yeah, you too.